We trust computers with basically everything, right? Our most important calculations. But what if I told you their math is, well, it's kind of weird. It follows these hidden, sometimes bizarre rules. So today, we're going to dive right into that strange world of computer numbers and uncover how these machines really think. Okay, get this. What if 7 plus 5 equals -4? I know, it sounds completely wrong, right? Like a major glitch. But it's not. And that little puzzle, that's the key to understanding a fundamental truth about how computers actually work. Seriously, this is not a trick question. It's a real thing that can happen, all based on the machine's own logic. So, in this explainer, we are going to solve this exact puzzle. And along the way, we're going to see how computers truly handle numbers. All right, to get to the bottom of this, we have to start small. I mean, really small. The absolute smallest piece of information a computer can even understand. Yep, we're talking about the bit. So what is a bit? It's basically just a tiny switch. It's either off, a 0, or it's on, a 1. That's it. And every single thing on your computer, I mean everything, from a text message to the most complex video game, it's all just built from billions and billions of these simple little ones and zeros. Okay, and right here is the first big clue to our whole puzzle. See, computers don't just see a never-ending river of bits. They group them up into these fixed-sized chunks, these containers called words. Just think of them as little boxes that can only hold a certain number of bits, say 4 bits or 8 bits or 32. And for our little mystery, we're just going to use a tiny 4-bit box. And this fixed size, this limited number of slots, oh man, that's where everything gets really interesting. And this right here, this is probably the most important idea of this whole explainer. A pattern of bits, it doesn't mean anything on its own. It's just a pattern, right? Ones and zeros. Its meaning depends entirely on the rulebook we apply to it, which means the exact same sequence of ones and zeros can represent two completely different numbers. Wild, right? So the first rulebook is for what we call unsigned integers. This is the easy one, the straightforward way. You just think of the bits as powers of 2. 1, 2, 4, 8. You know the drill. With this rulebook, all the numbers are either 0 or positive. No negatives allowed. So let's take a look at a pattern 1101. In this unsigned world, we just add up the places where we see a 1. So we've got an 8, a 4, and a 1. Add them up. 8 plus 4 plus 1, and you get 13. See? Simple enough. But what if we need negative numbers? I mean, we usually do, right? Well, for that, computers almost always use a system called 2's complement. And what's so cool about this is that the rule change is super subtle, but it's incredibly powerful. All it does is say that the very first bit, the one all the way on the left, it gets a negative value. Okay, so let's look at our exact same bit pattern, 1101, but this time we're using the 2's complement rules. That first one isn't positive 8 anymore. Nope, it's negative 8. So the math becomes -8 plus 4 plus 1, which equals -3. Whoa, same bits, totally different number. And this just shows you the whole idea perfectly. The only thing that changed was the rule book we were using. The bits themselves, 1101, they stayed exactly the same. But just by changing the meaning of that first sign bit, we went from a positive 13 all the way down to a -3. The computer just sees the pattern. It's the code, the programmer, that tells it which rules to follow. Okay, so now we have all the pieces we need to solve our big mystery. We know about those fixed size boxes, and we know about the 2's complement rulebook. Let's put it all together and finally see how on earth 7 plus 5 can equal -4. All right, first things first, the computer turns our numbers into its 4-bit system. So 7 becomes 0111, 5 becomes 0101. Then it just does basic binary addition, carrying the 1, just like in grade school, and the final pattern it ends up with is 1100. And here's the absolute key. The computer has no idea we started with 7 and 5. It's totally oblivious. All it knows is, hey, I just did a thing, and now I'm holding the bit pattern 1100. Its only job now is to figure out what that pattern means. So what is 1100? Well, if we're in a system that needs positive and negative numbers, like 2's complement, that leading 1 is a giant red flag. It's the sign bit. It screams, hey, I'm a negative number. So let's do the math again. That first bit is -8. The second bit is a +4. So -8 plus 4 That gives us -4. And there it is, the case is solved. See? 7 plus 5 is 12. But in our little 4-bit signed system, the biggest positive number we can even make is 7. Our result, 12, was just too big. It overflowed the positive range, and it wrapped around into the negative numbers, landing right on the bit pattern that happens to mean -4. It's not a mistake. It's the computer following its rules perfectly. Now, you might be thinking, okay, that's a cool little brain teaser, but does it really matter? Oh, it absolutely does. This exact behavior causes some of the sneakiest, most frustrating bugs in real-world code. Let me show you a classic example from the C programming language. So here we've got a super simple loop. It's supposed to count down from 10 to 0. But notice the variable I is declared as an unsigned int. Remember that? That means it uses the unsigned rulebook. It can only be 0 or positive. And because of that one word, this loop will run forever. Any ideas why? Let's follow the logic. The counter I counts down. 2, 1, 0. Okay, so what happens next when the computer tries to subtract 1 from 0? Well, since I is an unsigned number, it literally can't become negative. So it does the only thing it can. It wraps all the way around to the biggest possible number it can be, which for a standard 32-bit integer is like over 4 billion. And that's the bug. The loop's condition to stop is I greater than 0. But by its very definition, an unsigned number can never be less than 0. That condition is always true. So the loop just runs forever, probably crashing the whole program, a ghost in the machine, all because of that one little word, unsigned. So, wow. After all that, overflows, infinite loops, what's the big takeaway here? What are the key things you should really remember from all of this? Okay, first and foremost, bits are just bits. They're meaningless without a rulebook. Interpretation is everything. Second, those fixed size boxes for numbers create hard limits, and when you cross them, you get weird stuff like overflow. Third, as we just saw, mixing signed and unsigned rules without thinking, well, that's just asking for trouble and some really hard to find bugs. And finally, and this is the big one, what looks like a crazy computer error is often just the computer perfectly, logically, following its own hidden rules. You know, we've seen how the exact same pattern of bits can become a positive 13 or a negative 3. It all just depends on the rules. And that leads us with one last kind of cool question to think about. If these bit patterns can be interpreted as different kinds of numbers, what else can they be? What are the rules that turn these ones and zeros into letters, or the colors on your screen, or the music you're listening to? But that's a story for another time.